Okay, we're up to our next to last lesson on Taylor and Power series, and we're going to actually figure out what this idea of power series is, and this is AP Topic 1013. So it says we're going to take a short break from Taylor polynomials to talk about the bigger family that Taylor polynomials belongs to, power series. So this is kind of the bigger picture. Taylor polynomials are a subset of the power series. So power series is just any series that's built on terms whose power is increased by 1. So obviously our Taylor polynomials have been doing that. Every term increases by a power of 1 as we keep adding in the x minus c to the end part. So that end part keeps going up by 1 every term. Of course, that is what a Taylor polynomial does. A power series, though, is more generic. So a normal power series does not have the derivative part or the factorial part like a Taylor polynomial. So just a generic power series is just any kind of series where the terms increase by a power of 1. Okay, well, there you go. So what we're going to focus on for power series is this next idea. We get very interested in how far away from our center, our C, that our power series accurately represents the original function. So, you know, we've stated that we'll have some kind of original function, and we're trying to approximate it with some kind of series, and maybe it's centered right there. And we want to know, you know, how far away from that center, left or right, are we still actually approximating that function? So this gives us an R. It's called the radius of convergence. And we'll generally use the ratio test to find a series radius of convergence. So if the ratio test is less than 1, we know from last unit that means that the series converges, so it'll converge to whatever values we find for x that make the test less than 1. We'll see an example of this in a few minutes. Now, so what's going to happen? If the series only converges at C, so if the center is the only place that gives us a convergent value for the series added up to infinity, then we say that's a radius of convergence of 0. There's nowhere to the left or right of it that converges. In this case, the ratio limit test will be greater than 1, so it diverges for everywhere except for at the center. Now the series could converge in some kind of absolute interval to a number, r, the radius of convergence. In this case, the ratio test limit will equal some x expression. We'll see an example of this in a few minutes. Since the ratio test only converges for values less than 1, we're going to have to set that x expression absolute value less than 1 and solve for x to find out our radius of convergence, to find out the interval of our radius of convergence. That'll give us a compound inequality, and that'll be an interval that shows all of the r's that work. And then finally, a series could also converge for all of x. In this case, our limit will provide a constant answer without an x, and that constant will be less than 1. Since the constant's always less than 1, then all the x values will lead to convergence. So the radius of convergence is infinity. Now note, r is the number that represents how far from the center the power series accurately represents the original function. And then beyond that, we can't say for certain. All right, a little bit more, and then we'll look at an example. Now, whenever a power series converges up to this number r, we'll write it as an interval to show all the x for which our power series is accurate. You'll take your r, you're going to add it to x, that'll be your upper bound, and then you'll subtract it from x for a lower bound. And together, this all creates what's called the interval of convergence. Now, here's what's really important, is that those bounds, we don't know if they actually work or not. So this next thing says that you must test the endpoint of the interval of convergence, each endpoint, to see if they're included in the interval convergence interval. So your final interval will have some combination of parentheses and brackets to show if the endpoints are part of it or not part of it. You will test each endpoint by plugging its value in for x and then using your convergence and divergence tests from the last section, AP 10.1 to 10.10, and you'll go through your normal progression of tests looking for geometric series, p-series, alternating series, and then using the nth term test, ratio test, whatever else you need to do. And we'll write our interval of convergence as a compound inequality, including or not including the endpoints. So we might write it like this. with the number. You could use interval notation, whatever. Okay. So I'll come back to 5, 6, and 7 in just a minute. Let's look at an example of this. So the instructions might say find the interval of convergence. So you have to find the radius of convergence and then test the endpoints for this power series. And so I'm going to give you a power series. The summation from n to infinity of -1 to the nth, so it's alternating, x plus 1 to the nth over 2 to the nth. Okay, so the first thing we're going to do is we're going to use the ratio test, and we're going to find out, are there values for x that are less than 1. So here we go. Take the limit as n goes to infinity of, -1 to the n plus 1, right? We do n plus 1 divided by n, or multiplied by the reciprocal of n, or a sub n, I guess, the original function is what I should say. All right, and so that's the limit as n goes to infinity. And let's see, what can we do here? Well, we can pull out a -1 to the nth and a -1 to the 1. Whoops, there should be an n plus 1 here. I just added that in up here. I forgot that. Have an x plus 1 to the nth times an x plus 1. A 2 to the nth, we'll put all this together, I guess. A 2 to the nth and a 2 to the 1. -1 to the nth, x plus 1 to the nth. Okay, let's see what cancels out here. Those are gone, those are gone, those are gone. And let's see, it looks like we're going to have a absolute value of negative x plus 1 over 2. And of course that absolute value negates that negative x plus 1 over 2. Okay, so the ratio test says that a series will converge if the value is less than 1. So we're going to set that less than 1. And we want to solve for x now and find out what's the radius that works here. So I'm going to multiply 2. Well, actually, what we're going to do is multiply 2 on both sides and then subtract 1. And actually, I guess what I should do, I'm sorry, I set it up as a compound inequality. So because we still have the absolute value signs there, I should not have eliminated those. So still absolute value there. Get rid of the absolute value by creating this compound inequality. I went ahead and divided by or multiplied by 2 at the same time. Then we subtract 1, and we get this. Okay, so this is the radius of convergence between -3 and 1. However, what we don't know is we don't know if -3 and 1 are actually, if they actually make the power series converge or not. We don't know if they're actually included or not. So we have to test each of those separately. And so these take a little bit of work. So now I'm going to say, okay, well, let's test the left endpoint, the lower bound -3. So I'm going to go ahead and take a look at my series again from 1 to infinity, -1 to the nth, -2 to the nth, over 2 to the nth. Okay, is that right? Well, what did I do? I took my -3 and I plugged it in for x and got -2. So we're plugging in that x value to see what happens here. And what we need to do is we need to use our series test from AP 10.1 to 10.10 to determine this convergence. And one thing that we'll notice, I don't know if we've encountered this before, but a -1 to the nth and a -2 to the nth, basically those negatives negate each other because every power, a first power, is going to give us two odds that are going to multiply to an even. Even powers are going to give us those negatives. Two negatives that multiply to positive, I should have said. And then an even power is going to give us two negatives that can become even on each individual term. So we can rewrite this n equals 1 to infinity of just -1 No, I just said get rid of the negative 1. So we can get rid of the negative off the 1. So 1 to the n times 2 to the n over 2 to the n. And then what happens is those 2 to the n's, they cancel out. And of course, 1 to any power is 1. So doesn't really matter. We're going to take the series of 1 to the nth power, and what we know is that on the geometric, it's a geometric series, right? It's a number to an nth power, and we said if our number is 1, if you remember your roadmap from your geometric series, it diverges. So therefore, let me write it like this. I'm going to do 3 dots. That's shorthand for therefore. Negative 3 is not on the interval of convergence. So then we're going to go ahead and test the other bound, x equals 1, and we're going to plug that in for x way back up here on our original equations. So plugging 1 in there, 1 plus 1 is 2 to the nth, all over 2 to the nth. All right, well, those cancel out, so we get the series, the summation of negative 1. Oh, whoops, there's an n there. I forgot to put that in there, so let me add that in. Negative 1 to the nth. Okay, well, now it is alternating, and so you can say, what's an alternating series? But then you can say, okay, on an alternating series, we can do the nth term test. And so what happens is this goes to infinity. Well, we actually can't do that because we disregard the alternating part, so that doesn't help us out. So then I'm like, well, actually, this is just another variation of a geometric series. And we said on the geometric series, it's the absolute value of r, so that would be 1. The absolute value of negative 1 is 1, so 1 is r. And just like above, we said if r equals 1, the geometric series diverges. So this also diverges, so therefore 1 is not on the interval of convergence. So what's the final answer? The question is find the interval of convergence for this power series. We found out the numbers were negative 1 to 3, and we tested, negative 3 to 1, and we tested negative 3 and 1 and found out that they were not convergent according to all of our old series tests. So we use open parentheses on those numbers. Okay, there's a lot. You need to practice a few of these, and it's going to use your skills from the last unit with different kinds of convergence tests. All right, there's just a couple of quick notes to finish this idea up. The first is that you can integrate and you can differentiate power series because they're Bell-Taylor polynomials. Just integrate and differentiate each individual term using your normal calculus rules. And here's the deal, though, and this is an important thing to remember. You might encounter this on a test. The radius of convergence of your differentiated or integrated series will always be the same as the radius of convergence of the original series. But the interval of convergence might not. The interval of convergence of your differentiated or integrated series will not necessarily have the same behavior at the endpoints. Therefore, you're going to have to test those endpoints again, just like we did. So you might be asked to find the derivative of a power series and then list its interval of convergence. It's not going to be the same as the interval of convergence, or it could be. It doesn't have to be the same as the interval of convergence before you took the derivative. Okay, this is a lot. This last unit has some tricky stuff. You'll want to do the practice, maybe look at some other resources online and learn this, and there you go.